so you join Xerox, and you're coming onto his team, right? And what was kind of the first thing you worked on when joining?
Yeah, this was 1976. Well, first of all, I'll never forget during the on-campus interview, he showed me this thing called the Alto. I have one sitting next to me on the right here, and it had a bitmap screen, so you could do graphics, and it also had this 3 megabit Ethernet, and you could send a file or a whole disk pack between two machines in what seemed to be almost instantaneous. That impressed me, not so much the bitmap screen. But he hired me to help commercialize the 3 megabit Ethernet, which he and David Boggs had developed at PARC. By that time, there were probably 50 to 100 Altos working on a 3 megabit Ethernet. They had developed the first protocols. The email systems were coming up. There was a file server on the master time sharing computer called Max. Um, it it was like being in heaven. Now I technically was in what was called the system development division, which
Okay.
was set up to productize the Alto. But we were co-located with the people at PARC, so I got to know all the people as if I was working there. Butler, Lampson. So I started working with Chuck Thacker. I basically, what do we do next? And Bob actually set up as a goal to try to run at 20 megabits per second, which seemed a little aggressive.
Right.
We ended up running at 10. And we had analog people in the group. There was about four of us in the group that were going to design the entire workstation. What was called the Xerox Star
Hmm.
8010 professional workstation. And I started the first Ethernet I did was called the Xerox Dolphin, or D0, which was meant to be the productized version of the Alto.
Right.
And as a kid out of school, I learned rather quickly that Chuck Thacker, who's equal to about 10 normal people, he was just remarkably brilliant. He could design something in 1 minute that would take you half an hour.
Yeah.
He wrote his own schematic editor. He pulled the system together, and it was like 3 times as complex as the Alto, what I would call the Second System Syndrome. But my first job was to build an Ethernet controller for that system.
And so you mentioned D0, and then there was a kind of a series of these D star processors, right? And
Yeah,
there's D1, and then was Dandelion was the one that the Star workstation ended up being built
right.
on, right?
Yeah, the sequence was the Alto, the D0. The D1 was a slightly later machine. It was a pure Echo
Okay.
with ECL logic, extremely expensive and a lot of power. Like you didn't want to have one in your office.
Right.
It was probably like a 10 MIP machine. It's my watch today.
Right.
The Alto was probably a half MIP machine. The Dandelion, as you mentioned, that was the code name for the hardware that we designed. Um, it was maybe a half a MIP machine, but it was faster than the Alto because it had a faster memory system.
Hmm.
Uh, a huge difference between the Alto and the Dandelion was that in the Alto, Chuck had come up with a brilliant idea. I mean, it turned out um, on the TX1 back east, they had done this idea. But you have a bunch of hardware. And since hardware was, you're really trying to reduce the cost of the hardware.
Hmm.
And so he basically came up with a multi-threaded idea to share the CPU, and the microstore memory with all the devices. So the Ethernet controller, the display controller, the disk controller, low-speed I/O had microcode that did most of the work there, and the hardware was just small buffers, enough for a few words from the disk or a few words from the Ethernet, and the devices would, like on a normal bus, compete in priority order, compete for access to the CPU,
Hmm.
and one of the challenges with that Alto design is that your microcode could keep control of the CPU as long as you wanted.
Right.
You had to relegate, you had to let someone else fight for control of the CPU. And that was an interesting experience for me because I was writing the microcode for the mouse, for displaying the mouse on the screen at the time.
Oh wow.
And it would stopped working, and I would go look at the other microcode, and Chuck Thacker had spent too many cycles trying to get his microcode to work. So I said, Chuck, you're not giving me the cycles just for the mouse to track. And so he'd go fix his, and then mine would work, and then he would go change his again, and mine would stop working.
Right.
So so Butler Lampson, who was the brilliant, I don't know, savant at PARC, everything, but operating systems and compilers and languages, and he got familiar with hardware there. He came up with a design called Wildflower. He actually wanted to have a design with like 0 chips in it, which, because he saw the D0 had gone one way. Let's try to make it even more focused.
Right.
And he had an idea where you should schedule fixed rounds for the microcode so the display always knows when it's going to run. The Ethernet always knows when it's going to get a chance to access the CPU and main memory. Brilliant idea. Computers aren't generally designed that way. Usually it's a bus, and you, like I was saying, you ask for service, and if you don't get service, your buffer underruns or overruns.
Right.
And it's like, why do these computers work? I mean, they don't at a certain point. But this system, this idea, where there's guaranteed access to memory in the CPU on a regular basis, meant that if the processor met its cycle time, I/O would never get an underrun or overrun. So that concept that Butler came up with, we adopted that in the Dandelion. It basically followed the ideas that Butler had in the Wildflower, and we implemented that in the Dandelion. The Ethernet got 2 slots, the display got 1, the disk got 1, low-speed I/O, which is based on 8086, 8085. Kind of later took over the world.
Right.
So we knew we designed the Dandelion that if we met the cycle time goal, which was 137 nanoseconds, the fine structure of constant physics,
Right.
that it would work. And what a great project to work on.
Right. So if you're, the way I'm kind of like conceptualizing this is you're essentially like checking sort of like each slot each time through. Is there a performance penalty? Like, let's say you have a scenario where just one of those devices or peripherals or whatever you like to call it, one of those slots is the only thing that's active and doing anything. Are you paying a cost for kind of like checking or having each of them kind of occupy part of that loop there?
Well, if you don't have any I/O to move to or from memory, you don't ask for your slot.
Okay.
And then if no one takes that slot, it goes to the emulator, the language emulator.
Okay.
So in the case of the Alto, well, it's not slotted like this, but the language emulator was always lowest priority. So it ran the Nova instruction set, the Data General Nova instruction set. By the way, I have a Nova computer behind me there. You can see that's from the soul of a new machine.
Right.
Novas were around PARC before they designed their Alto. And then they built a Smalltalk, the language Smalltalk that Alan Kay and his company designed, and Lisp. And so you could kind of tailor the CPU for the instruction set that you wanted. And for the Dandelion, we just did the emulator for the Mesa language, which was a language designed to Xerox PARC. Didn't go anywhere after that.
Right.
It was the basis for all our machines. A very strong type checking language, kind of some aspects of object-oriented programming. Just a beautiful language, but it didn't have enough users to survive.
Right. Is so looking at the kind of on PCB or the architecture, the chips on the board for the Dandelion, it was a bit slice architecture, right?
Yes, we won't be able to see it if you're listening to the podcast, but this is the actual CPU card.
Wow.
There are 4 AM2901, 4 bits each, so this is a 16-bit computer. And then the control store is at the bottom, 4K 48-bit words. And that is enough to cause a lot of trouble.
Right.
You could get, with a writable microcode, with a writable control store, what a field day for the language designers.
Right.
So they would run applications, representative applications, and re-encode the Mesa instruction set, the byte codes, almost every week to see if they could get the code size smaller, because
Oh yeah.
in the Dandelion, we weren't sure if it'd go out with 128 kilobytes of memory, 384 kilobytes of memory, or maybe even 512 kilobytes of memory. And there was just so much functionality. I mean, it was a GUI.
Right.
There was email, there was networking, there was storage. It's remarkable how much functionality you could put into just half a megabyte of memory.
Right.
Just remarkable. Now, there's all one unprotected address space. There was no user and kernel. But it was, so the classic CISC, complex instruction set computer,
Right.
they could redesign it on a weekly basis and get the code size down. There was even one point where they implemented microcode swapping. You could swap microcode in and out of the microstore.
Wow. Wow.
Just kind of the pinnacle of CISC at the time.
Right. And so the reason why, kind of like looking back, the computers were designed in this way at this time, right, is because it was too expensive or not possible to have, a single integrated microprocessor, right? And so you mentioned the 2901, which I believe was kind of the control chip, and then there was all of these 2900 logic chips that you'd chain together depending on whatever the width of the logic that you were doing. Is that right?
Well, the 2901 was the ALU, so these were the ALU chips. Everything else is just decoding the instruction, the program counter, accessing the microstore, talking. This has the microtasking hardware so that the different microcode can run. So you have to save the PC for all the microtasks. That's basically about it. But fundamentally, we'll get to Spark and RISC, but I mean, now's a good time as any, since we're talking about architecture. I mean, fundamentally, the people at PARC were certainly aware of caches.
Mm-hmm.
IBM had implemented some caches on their very high-end 360s, the Model 195. But caches would just add more cost.
Right.
Significant more cost. And without a cache, you're limited to main memory access, which is, in the case of the Dandelion, was 3 micro instructions. So during one of those slots I was telling you, where the microcode could get access to the CPU and memory, it could do one memory operation. Mm-hmm. So now you've got memory running 3 times slower than your basic instruction. Whereas in RISCs, you have single cycle, if possible, loads and stores. And that's because you have a cache.
Right.
You can get to the cache typically in one cycle. And caches just were not in the cards at this time. And no one knew what the best instruction set looked like. So that having a writable control store gave the flexibility to, especially as a research institution at PARC, to explore that. What are some, of course, there are an infinite number of programming languages.
Right.
It would have taken the age of the universe to answer that question. But, as a research vehicle, it was a great thing. Now, as a product, it meant you could also, in the field, upgrade the microcode if you needed to. If there were bugs or you needed some new feature. There are some very complex instructions for process switching. So there were lightweight processes, and there was microcode for procedure calls, saving the arguments away and all that kind of stuff. It was a stack-based architecture, Mesa, unfortunately, and stack-based architectures have very slow execution times,
right,
compared to others. In fact, Forrest Basket once came around with a little benchmark called Puzzle, and he ran it on our Dandelions. It really sucked.
Yeah.
We were like so slow.
Right.
It's like these guys, developed this beautiful language, but no one had ever looked at how slow it was.
Right. Right.
So I learned a lot of lessons there.